Well, thank you for attending the fifth webinar in the series of 6 roof hugger metal over metal retrofit systems webinars. We do these twice a year. This is the 5th one out of the 6. And this one actually is probably one of the most important ones in helping people understand what is involved in the design of a metal over metal retrofit system using roof hugger subframing systems. Again, thank you for attending, and we hope you get something out of this, which we are sure that you will. So let's get started. My name is Mark James. I represent Roof Hugger LLC. I've been involved with the company for 11 years directly now. And actually, before that, for several years, I was one of their largest customers purchasing retrofit subframing systems from Roof Hugger and shipping them to jobs all over the country. Roof Hugger's been around since the late 1980s. They formally were introduced into the marketplace in 1991. And in 1994, they acquired their very first patent on the factory notched sub-purlin, if you will, or subframing systems. Today, we have several patents on systems as well as a multitude of different types of products that will address any type of existing metal roof over primarily a pre-engineered metal building system. So with that, let's get started. This is a copyrighted presentation. However, we can't share the presentation in PowerPoint form, but we can provide you a PDF copy of the presentation by just sending an email to mjames@roofhugger.com. We will be glad to send you a PDF copy of that. Just send the email off and I'll send it right back to you. So what controls subframing a new roof design? Well, governing building codes and required design loads and so on and so forth, they control the design of any type of new construction roof as well as a retrofit roof system. The building exposure to the wind and the elements, the building occupancy, and very, very important, the importance factor, which I'll explain in the next couple of slides. That is of the utmost importance. Existing roof geometry, slope, and height. Existing roof support system and purlin spacing. Drill that down, that really means existing Z-purlins, C-purlins, commonly used in pre-engineered metal buildings, or even bar joist systems that are used in wide bay systems and so on and so forth. Roof Hugger's products are explicitly designed to go over secondary structural framing, steel framing, as found in pre-engineered metal building systems. Wind uplift or negative pressure at various zones of the roof will control the spacing of the subframing that we provide, as well as other things, meaning the new metal roof that is chosen to go on the job. Now, wind uplift is very easily explained. Basically in a standard less than 1 on 12, 1.5 on 12 pitch roof, you have 3 zones. The zone 1 is the lowest load on the main field of the roof. Zone 2 is at the perimeter or the edges, the gable edges, as well as the eave, along the eaves. And then the highest wind zone area is typically in the corners. When wind blows across a roof, regardless of the direction that wind is, really doesn't have anything to do with prevailing winds. But whenever the wind blows across a roof, it creates a section. That's where you get the term negative pressure. And essentially, when wind blows over a metal roof, it wants to pull that roof right off of its structure itself. by that suction or negative pressure. Roof design basics. First of all, let's understand that most of the buildings that are being retrofitted with metal over metal subframing systems, they're older buildings, and those wind speeds that were used during the construction and the initial installation of the building, they have increased over the years, and quite dramatically actually, where there used to be some 70-mile-per-hour wind speeds in the United States, there aren't any anymore. I think the lowest wind speed is required at this point in time is about 80 miles per hour, and that's on the extreme west coast. All the way up to 155 mile per hour wind speeds along the Gulf Coast, southern Florida, even inland areas as much as 120 to 130 miles per hour, as well as high wind loads in the eastern seaboard of the United States. Older roofs are normally subject to new code requirements when being replaced or being retrofitted, as in a metal over metal retrofit system. And today, most metal roofs require additional subframing in the edge and corner zones to satisfy this increase in negative pressures. The negative pressures are actually determined by engineering the design in accordance to the code mandates, but actually it's determined by controlled third-party laboratory ASTM E1592 testing that determines the wind uplift capacity of any new metal roof system. Virtually every metal roof manufacturer in the United States has gone through this testing on every single product, even from a difference as far as rib spacing, gauge will make a difference, and of course the different types of seams, whether they be through fastened or even standing seam roofs. On a through fastened roof, the panel screw frequency can increase the higher the wind speed, and of course on a standing seam roof, that clip spacing will get closer together to satisfy this negative pressure. And the attachment to the new structural framing, or in our case, to the new subframing systems by Roof Hugger. Appropriately applied ASTE 07 specified safety factors are based on a building's importance factor. Let's just consider a school versus, say, a warehouse or an office building. A school has a much greater importance factor. Thus, it has a higher safety factor that has to be applied. In many cases, when the wind uplift testing that is performed in an ASTM E1592, the capacities of that new metal roof system may be reduced by as much as 50%. Now, the ASTM E1592 is a simulated negative pressure test protocol. It is, in the photograph here, you see a 10-foot wide by 20-foot long test bed. Those three steel things in the center, those representative of 5 foot on center structural purlins, where the new roof that's going to go over this test bed is actually going to attach to that. Now, in some testing, they will reduce that spacing to 2'6", and even in some cases down to 1 foot on center. So you can see where there'd be a lot of attachment. Typically, an ASTM E1592 testing protocol will require 3 separate individual testing to get a total array of testing capacity and uplift pressure capacity. Now, as you can see, that test bed now is covered with some high or very thick polyethylene sheathing, and that's where that old term airbag test actually came from. Now, what happens is once the new metal roof is attached to that over the polyethylene sheathing, it actually is air is introduced into that chamber or that test bed from the underneath and actually creates an uplifting pressure simulating a negative pressure. As you can see in this particular photograph, you can see that 150 psf. The air that is being inserted into that test chamber is equivalent to 150 pounds per square foot of air pressure. Typically, standing seam metal roofs will fail between 85 and 110 pounds per square foot. That's based on a 5-foot purlin and clip spacing. Most roofs will fail within that range. Some roofs will fail in less than 85 pounds per square foot, and very, very few will actually make it above that 120 pounds per square foot. So I think what's important there is to understand that not all metal roofs are the same, especially from a testing. Now, here's a photograph of that particular roof, not the same one that was in the previous photograph, but this is a photograph of a 16-inch on center vertical rib standing seam that has failed. And the ASTM E1592 negative pressure test protocol requires taking the roof all the way to its failure point. The typical failure modes are seam disengagement or clip separation, where a two-piece sliding clip will actually disengage itself and come apart or separate, or the seam itself, once the seam, whether it be a 90 degree seam or 180 degree seam or even a 360 degree Pittsburgh lock type seam, actually engages or disengages itself and fails. The test result values are all subject to a safety factor based on the design criteria that has been specified. Now, let's get into some basic roof designs and what happens on, say, a gable roof. Now, I've taken a 50-foot by 100-foot building that's illustrated in this schematic here, and you can see that this particular roof has a new 24 gauge standing seam in accordance to International Building Code 2006, which that's no longer applicable in today's design. It's actually been much improved, but this is strictly as an example of what happens to a roof. In this case, a 50-foot by 100-foot roof. It's subjected to a 90-mile-per-hour wind speed and exposure C, general occupancy, which could be any type of building other than a school or hospital or any type of building like that. And with a 1-on-12 roof slope, which is very, very common in pre-engineered metal buildings. You can see in this case that the interior or the field of that roof on a 90-mile-per-hour wind speed, given on this particular metal roof that was evaluated and investigated, the panel clip spacing on that standing seam would be 5 foot. But in the edges, it would actually only be 3.9 feet, and in the corners, 2.2 feet. Now that's really knocking it down very, very close. And those corner zones, which again is a calculation based on the engineering design, would be a 5 foot by 5 foot area. Then the edge strips would actually be 5 foot by however long it is along the eave or however far it is up that gable end of the roof. Now, this is a problem. Most metal buildings in yesteryear, if you will, had a purlin spacing of a maximum of 4 or 5 feet. Up in upper climates, when it was subject to greater snow loads, it may have been 4 foot, or even maybe a little less in the extreme upper climates of the United States. But 5 foot would have been very, very common in the lower United States from a design. I know the metal buildings I was involved with even going back 40 to 45 years. In the southern U.S., all of them had 5-foot purlin spacing. And somewhere along the early 1980s, that started changing, and you may get a 2'6" spacing along the edge of the roof and in the end bays of that roof, depending on the wind speeds. Anyway, remember some of this. Now, here's the same building with a steeper slope. This building here had a 1/12 roof pitch. This building has a steeper slope, and this uses the same design criteria and is subject to the same uplift pressures. The gable roof slopes over 1.5/12 will include an additional high pressure zone at the ridge of the building, almost identical to along the eaves of the building as well. Then you actually would add 4 more corner zones at the apex of the ridge at the gable, and those would be 5 foot by 5 foot as well. So dramatically, it does change. Now remember this 2.2 feet for the next slide. Now here's a comparison and a selection of which metal roof system by which manufacturer should we go with. Here's the same building under the 90-mile-per-hour wind speed. Same design loads. Let's increase the wind speed to 100-mile-per-hour wind speed instead of 90 miles per hour. Well, you can see the difference. Here's the pressures of the 90 mile per hour, 1931-47. In 100, that's increased to 23, 39, and 58 pounds per square foot. Well, look what the corner zones did. They went from 2.2 feet to 1.28 feet. So can you imagine having purlins basically every 15 inches on center from that standpoint? So that's a lot. But remember this, on a 58 pound per square foot uplift pressure, the tested value of that metal roof would have to be at least 116 pounds per square foot because of the safety factors, and that 116 being decreased by 50%. Not all metal roofs are created equal. Now I'm going to show you 2 different manufacturers. I won't share with you who they are, but they do vary from one manufacturer to the next. Manufacturer A, same wind zones, 100 mile per hour wind speed, same everything. Now you can see the pressures are the same, but look, manufacturer A was 4.81, and in the corners it was 1.28. Manufacturer B has a stronger roof. 5 foot in the interior, 5 foot in the edge versus 3.12 for manufacturer A, and 4.64 in the corner zone. So from a subframing standpoint and material cost standpoint, if you selected manufacturer B's standing seam metal roof system, it would be less money than manufacturer A because of the subframing system, the fasteners, the clips, etc., 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 and labor savings. So I hope that explains to you the differences between manufacturer A and manufacturer B. And we could add a C in there and even get another one. But as I said earlier, most metal roofs today will require, at the very least, additional corner zone framing. Now, just quick look on a single slope or monoslope roof. Same design criteria, building dimensions. Slopes are over 2/12. You can remove the number 3 corners and reduce the number 2 areas. But you get really about 5 zones on a monoslope, and I've always used this comparison. If you think of a monoslope roof, think of an airplane wing. Now, what happens on a hipped roof? Well, basically the same thing, except for you get edge zones along the hips, which are both sides of those hips. You get corners, especially in the four corners of the roof, but everything's the same. Now look at the 1.87 feet in the corner, same design criteria, etc. Now, things that you can do from a design and construction standpoint is you can select the stronger panel system from your preferred manufacturer, or you can select a new panel system from a different manufacturer. We're not trying to tell anybody to jump off the boat with one manufacturer and go to another. Just inquire with your preferred manufacturer what metal roof system could work better to reduce the amount of material required as well as the amount of labor required to install that material. You could actually explore 22 gauge versus 24 gauge in a standing seam. However, you won't get a dramatic increase in uplift pressure capacity, but you will get some typically. You can choose a 180 or 360 degree seam in lieu of a 90 degree seam. For all intents and purposes, in high wind zone areas of the United States, 90 degree seams are really not used very much anymore because of the wind speeds that they have to satisfy in the design of these new metal roofs. So, corner and edge zone framing. Well, what can we do? So, based on that new metal roofs, ASTM tested capacity, additional corner zone or edge zones may be required. As you can see in this photograph here, that is a hip roof, and you can see and identify the spacing of the subframing in the yellowed area that I've shown versus the area in the main field of that roof. In that main field of that roof, that particular spacing is actually 5 feet on center, and it was knocked down to 2'6" on center, all the way along the edge, along the ridge, and along the hips itself. So, high load conditions often require intermediate framing that roof hugger has. We call that, we've tested this system, it's called integral framing. It works in harmony with the Factory Knots famous roof hugger sub-purlin system. And as you can see, we have these struts, and these struts go from eave up, depending on the design. This is a typical corner zone you can see in this photograph. We have spaced these struts that go from the eave up to a certain distance or up to an existing purlin line, which in the foreground of this photograph, there's an existing purlin directly under this particular hugger sub-purlin. Then 5 foot downhill, you have another existing purlin, and then it goes into 2'6" spacing in that corner. On the right-hand side of that photograph, each one of these huggers right here is in fact a 5 foot spacing or an existing purlin directly under those hugger sub-purlins. This particular job is actually in Houston, Texas. It was at the Intercontinental Airport there on a warehouse building. In very high loads or panels that have not been tested with integral huggers, they may require a taller, what we call a hat grid assembly, to provide necessary panel clip spacing. And in this particular case, this is actually a project in Baltimore, Maryland at the Port Authority there. And you can see this buildup of hats going up the roof as well as across the roof to actually be able to receive that required clip spacing of that particular metal roof that you see being installed. Now, one big item that you need to see here, if your metal roof system that you've chosen has not been tested in a third-party laboratory using roof huggers integral framing systems that we showed in the previous slide, then we'll be forced to have to actually do a hat grid system in whatever corners or edge strips, edge zones that may be required based on the governing building code and wind speeds. Now, so what's the problem with that? Well, this is a standard 12-inch on center rib panel roof with probably a 1 1/4, maybe a 1 1/2 inch tall major rib. And you can see the height of these huggers in this field over this particular rib panel roof. Well, that height of that roof hugger subpurlin had to be increased to come up to the height of this hat grid system that we installed. It increased the cost of the subframing extensively on that particular project. So here's a question that comes up all the time. Adding weight to the new system, or the new assembly of a metal over metal retrofit, which includes, of course, the subpurlin subframing system, as well as the new metal roof. Well, what happens when you add all that weight of the new metal roof and subframing system to that existing building's roof? Great question. And this is a legitimate concern that any design professional and contractor really should investigate. You know, the big question is, are you sure the existing building can support this added weight? Can that existing building receive an additional 2 pounds per square foot on top of its existing roof and actually be in accordance to the governing building codes? Well, Roof Hugger has tested these systems, and we have underwent some third-party AISI protocol testing to determine if our Z-shaped factory notched roof hugger subpurlins increase the strength of the existing building purlins. Well, good news is it did. Now, the total weight of a new metal over metal retrofit assembly that's being added to that existing roof is very close to being 1 1/2 to 2 pounds per square foot. It may exceed that based on adding insulation, whether it be fiberglass or rigid board insulation, or even the height of the subframing system may increase that weight, but typically never over 3 pounds per square foot. So, legitimate concern. So this AISI protocol base load testing proved that we can strengthen the testing. This is actually a copy of the purlins, or a photograph of the purlins that we tested after putting a roof on over this existing purlin, or these purlins. And that was what happens. It crippled the existing purlins. And we had to do that to see what its failure point was. And then we would attach the roof hugger system on there to see what its failure point would have been. Well, the good news is, based on a 25-foot maximum span or base spacing, the gravity load, or the dynamic additional load, could be increased up to 42% on the gravity. That would actually represent, on an 8 by 16 gauge purlin spanning 25 foot in a bay, the gravity load could actually go to an originally designed 20 pound per square foot live load. It could actually kick that existing purlin up to about 28.4 pounds per square foot. Now, everybody needs to visualize when we're talking about this. Visualize this. You have an 8-inch deep Z-shaped 16 gauge purlin. Let's look at a cross-sectional view of that. Now let's put the old metal roof on top of that, and then let's put the factory notch roof hugger subpurlin on top of that. And let's say that that subpurlin is 2 inches tall. Well, you have the 8 inches of the existing purlin, and you're adding a 2-inch Z-shaped roof hugger subpurlin on it, and essentially you've extended the depth, the total depth of the structural frame or structural purlin to about 10 inches in lieu of 8 inches. It's that simple, but it's a lot more involved from an engineering, design, and calculation standpoint. Wind uplift up to 85% increase, and some of these you have to understand that the chart that I'm showing you indicates the results of a certified gravity and uplift load test that we performed in 2008. These results show the increased strength in load values when the roof hugger retrofit system was used. And as a disclaimer, hungers, when attached for the appropriate detail, will typically add more capacity to the existing purlins than the additional weight of the retrofit assembly. I'll repeat that. More additional capacity than the additional weight of the retrofit assembly. Huggers may add capacity above this amount, but additional investigation of the existing framing will need to be undertaken, meaning once we've increased the capacity of the secondary roof purlin system, you are adding weight to the primary framing of that building, and that would need to be investigated and evaluated by a professional engineer. So how do we do this? Our roof huggers are considered continuous. We lap them basically 2 inches at every end, and we attach them and attach the 2 at every end with 4 standard screws. And they're number 10 pancake head screws. So that basically you're getting a continuous sub-purlin system. So framing anchorage, and I like to bring this up, when you do a roof hugger sub-purlin system, you're going to put a lot of screws into that existing roof structure. Roof huggers factory notched sub-purlins are pre-punched in the factory for up to 3 fasteners in the foot of between each major rib. The quantity of fasteners will be determined by us if in fact you request us to design the subframing system. But remember this, we attach it from a structural standpoint, and roof hugger subframing systems are structural systems. They are not guessed at, and they are not shipped out in the field for somebody to put a screw every once in a while. Now, the upper left-hand corner is a tall clip system that has a lot of limitation. You can see back in the right-hand side over where the installation is. This trapezoidal standing seam was attached to the existing purlins with a taller clip, and a wind came along and literally blew that roof right off of the clips. The clip stayed for the most part, but it didn't. Now, here's a bottom right-hand photograph. Here's somebody came in and they screwed a 2x4 over the existing rib panel roof that you can see a little bit here. They put long screws, you can see the screws sticking up here, into the existing purlins. And then they came in and put a 24-inch on center trapezoidal standing seam with its clips. That blew off as well. And here is a hat channel system that was probably less than a 16 gauge, may have been a 16 gauge hat that ran across the existing major ribs of a 12-inch on center rib panel, and they used a long fastener, and it was not a continuous bearing type roof system or sub-purlin system, and that wind blew that thing off just like it wasn't even attached. So anyway, that's going to conclude this program. And again, I remind you, if you wish to have a PDF copy, you can send an email to mjames@roofhugger.com. And again, thank you very much for attending. Our next program and presentation is on how to add energy benefits to a metal-over-metal retrofit in using roof hugger subframing systems. Actually, will be coming on in 1 week. Thank you again.